Hi, welcome to DV Club today on 5th of September. We'll have a special session on cache coherency verification. Again, this was requested by one of our DV Club members. Today we have 145 attendees from 83 different companies in 23 different countries. And our agenda today, I'll get on very quickly so David can start his presentation. We have David Kelf from Breker Verification Systems, Alex Netterville from Synopsys, and Nick Heaton from Cadence Design Systems. And we will finish at 1 o'clock. Thank you. And quick thank you to our sponsors, Agnesis, Cadence, Synopsys, Breker, Impress, ARM, and ST are our venue sponsors, and Tessol hosts DV Cup. Thank you very much, and we'll go straight to our first speaker. Okay, Dave, do you want to share your screen, please? Okay, do you want to go full screen, Dave? Oh, perfect. Okay.
I should unmute myself. Go ahead, Mike.
Our first speaker today is David Kelf, who's a regular speaker at DV Club. He's from Breker Verification Systems, where he's the CEO. The title of his talk today is Enter the Kaleidoscope, the Diversity of Coherency, Stimulus and Coverage. Dave is a well-known EDA industry participant, having run Cadence's verification marketing, driven Synopsys verification strategy, and run marketing for co-design, SystemVerilog, Novas, Verdi, and others. He is the CEO at Breker, who are focused on PSS-based SoC verification. He has a solid engineering background, has performed many ASIC designs, and holds a microelectronics MSc from Brunel University. He's from Boston, but today I think he's back in the UK just for today. Over to you, Dave.
Thanks, Mike. So morning, everyone, morning, afternoon, evening. So what we would like to do in this next 20 minutes is talk about a very effective way of handling coherency verification, which, as I'm sure most people on the call will know, is an extremely complex subject. What I've done is actually picked up a workshop that we often provide for customers, which is like 250 slides long, that gets into all kinds of detail on this. So I've tried to just pick out a few of the slides and the techniques that we use to give a sense of what has to happen for coherency verification, and and some of the ways you can tackle it. I think if people are interested in really learning more about this, feel free to contact Breker, info@Breker Systems, and we can provide the whole workshop, but it takes about a day or so to go through it. Anyway, so let's talk about coherency verification. So as we know, many people still think of testing cache coherency as this simple cache structure on the left-hand side here, where you might have just a small number, or even just one CPU, an L1 sort of high-performance cache attached to the CPU, a shared L2, and then an L3, which is like general storage. A modern SoC these days is, of course, far more complex. Huge range of CPUs with their own L1s, and then some shared L2. Usually some kind of fabric, like a NOT these days, with an L3 connected to that. And then we see such things as accelerators, DMA controllers, the MMU in a processor. We're seeing more and more coherent I/O, CXL being a good example, which is a coherent protocol built on top of PCI Express. We might have GPUs and other large accelerators or specialized processors, DSPs, with their own cache. And nowadays, we're starting to see more and more chiplet interfaces in this new UCIe, Universal Chiplet Interface Express standard, which is a coherent protocol-based standard, again, built on top of CXL, which allows for this high-performance communication with low latency for chiplets. So we're dealing with coherency with all these masters on a bus, lots of clever and complex memory structures, and somehow we have to make sure that we maintain coherency right across that entire system. And it's hard. So let's talk a little bit about how we cover this. The other thing I'll mention before we get into that is, of course, ARM and Intel you know, in the past, and other companies, AMD and others, of course, did a really good job of verifying for coherency their processes, and they put a lot of resources and investment and time into this. Nowadays, we're starting to see RISC-V, and RISC-V is, you know, it's a fantastic development, of course. I think everyone's very excited about it, but you know, for companies building RISC-V processors, for them to do the same kind of testing that ARM might put in, for example, into their processors for coherency, is right now at least unrealistic, especially given the size of the new apps processors coming out that we're starting to see emerge. So RISC-V introduces a whole new dimension into this, including, you know, specialized accelerators in the form of custom instructions that require their own coherency issues as well. So this is something that Breker has put a lot of effort into. I'm not going to sell Breker here, but just give you a sense of, you know, as we've built up the SystemVIP that we use for this, we've sort of allowed for some of these new developments. So Breker has a big SystemVIP library, and the most important one of these is indeed a coherency SystemVIP TrekApp, we call it. And this is a comprehensive set of coherency tests that use a broad range of algorithms across different configurable memory structures to do a very comprehensive coherency test. And this is the basis of what I'm going to be talking about today. I'm going to rush through this fairly quickly. There's a lot of detail here. It just whets an appetite to give you a sense of, you know, what could be involved in a coherency plan. So the way we look at the coherency test strategy is we break it into 3 chunks. The first is looking at clever ways of allocating memory, and this might include, you know, just regular allocation, which is designed to trip up and create verification bugs. But it also, in terms of coherency, we might do random allocation, repeat allocations, do special memory strides, that is, striding across memory addresses in different ways, target specific hash tables, and so on. So we take the allocation problem, we combine that with a scheduling problem, where what we try and do is schedule reads and writes and loads and stores across these different memory blocks, trying to pick out true and false sharing issues between the cache lines. Hopefully the terminology I'm using is familiar to some of you, but if not, we can get into more detail on that. So cache line, for example, is the data that's spread across the, you know, up through the levels of cache. So, you know, false sharing, true sharing is a very real issue, for example. We need to worry about things like that in the scheduling part of the strategy. And then what we do, we layer on top of that a whole range of memory operations. So these can be, you know, straightforward reads and writes, of course, but it could get into, you know, specialized load store, DMA type operations, atomic operations on memory, and so on. And the way we do this is we set up a very large portable stimulus graph. This is the top level version of the basic graph. And you can see on the left-hand side in blue there, the memory allocation strategies, which can be employed and selected randomly or directed. The different algorithms in the middle that we might apply to actually target the different memory. You can see things like Dekker in this little box here at the bottom. And then the different instruction sets that we can select. And you can see here that mostly the RISC-V instructions and some of the ARM instructions that we can select from to actually target and perform operations on this memory. And the idea then is all this is hierarchical, of course, but we can randomly work through this graph over and over and over again and generate a broad range of tests for this. The tests are applied to, I'm going fast for this bit, so I want to get into some of the coherency tests themselves. They're applied both using software-driven tests onto the different CPUs and at the same time transactions onto the I/O for those coherent I/Os, you know, to provide DMA access, whatever it is. And a key part of this is that the tests are made concurrent. So if you look at this simple SoC, what we can do is work through a graph and provide serial tests like this, one after another. But we can also stretch tests across a range of software threads combined with multiple transactions. So we might take a first test and run it across 3 different threads on 3 CPUs, do the same with a second test, a third, a fourth, fifth, and so on. And by doing this, what we do is we torture, essentially, the SoC And if we cleverly design this, we can throw up a lot of extra bugs and complex problems that won't be revealed if we just run one test after another. And of course, all these involve memory, so we can allocate memory and then reuse it in a very imaginative way, shall we say, to actually trip up the coherency type issues like this. Okay, so let's talk a bit more depth about coherency itself. So there's a number of metrics that we look at when we are trying to test for coherency. And the idea is to perform some kind of coverage that's designed at the system level. So it's no good, of course, using something like an implementation coverage. Maybe toggle testing every bit of memory is not going to point out anything useful to do with coherency. What we have to do is think about the high-level goals of maintaining a coherent system and what that involves. So these are the kinds of metrics we look at: transitioning between cache states, how we're doing snooping, how we're doing cache line sharing, false and true sharing, eviction cases, and so on and so on and so on. I'm just going to touch on some of these now. And again, I'm sorry to go so fast, but if I will provide this presentation on the TestSolve website here, and if you want much more detail, please feel free to contact us. So to transition between different cache states or cache line states, some kind of protocol is required, and the probably most common one is called MoesiStates. And what this does is it basically sets up 5 possible states that a cache line can get into. So what we want to do is we want to take that state machine on the left-hand side here, and we want to transition between these different states for specific cache lines using the multiple threads that we just mentioned before. And then what we want to do is repeat these tests for lots of different cache lines all at the same time. So we end up with a whole range on the right-hand side there of these transition scenarios for different cache lines, all executing concurrently. And what this does is it sets up, and here's a real version of this on a RISC-V environment. Heart, by the way, is a hardware RISC-V thread. And this is how we can execute multiple threads all concurrently at the same time on RISC-V. So what you see here is a whole range of cache lines all being executed all at the same time using the MoesiStates protocol. We can generally create very, very complex and very sort of bug tracking types of situations and scenarios with this kind of mechanism. We can go through cache line sharing. And so this is where, 2 masters or multiple masters share data in the same cache line, in the same block of memory that's been allocated, for example. And you can have true sharing, where they're just basically sharing the same data, or false sharing, where they're sharing data in the same block, but it's not the same data. And a lot of false sharing can lead to a lot of performance issues, of course. So that needs to be eliminated and checked as much as possible. And there's a lot of mechanisms usually built into a processor to test all this. So what we need to do is verify all of that. And to do that, we have to run across, again, one of these state machines or a series of state machines and execute these concurrently as well. So you end up with a graph a bit like this, where you can configure and set up different sharing options and try out basically false sharing and true sharing on this kind of a graph, on this kind of a mechanism. You saw the idea of snoops coming up here. So a snoop, of course, as you probably know, is a situation where a mechanism is looking at transitions on a bus and trying to figure out, do we need to actually, swap cache, flush cache, do things like that based on this transaction for particular cache lines that the snoops are monitoring. Snoops can get very muddled. So we actually have an algorithm we call Snoop Storm, based on something a customer is working on, which tests dozens of Snoop calls and Snoop filtering all at the same time to try and figure out, okay, what kind of Snoop sort of scenarios can we set up and sharing scenarios that can control. And again, this can be configured on a graph like this. Capacity eviction cases, this is where the amount of data in a particular line exceeds the amount allocated and the size of the line allocated. And so again, eviction tests very, very important. And what we can do is set up all kinds of different allocation strategies and drive some eviction cases and see how that plays with all the other types of tests we've been talking about before. And memory ordering is another issue. So here, what we're trying to do is create essentially a hazard, right, where one process is writing to one chunk of memory or one cache line, while another process is also writing to it, and then they're reading, and we're trying to set up a classic race condition, essentially, this kind of thing. One way of testing this is a public algorithm actually created by Dekker, where he creates all kinds of different hazards and mechanisms for that. And if we can combine a lot of these Dekker algorithms, we get a test that looks a bit like this, where we're doing all kinds of reads and writes designed specifically to create hazards across the memory system. And it's surprising how many bugs this finds. The Dekker algorithm is a really key part of the testing environment. And there's other algorithms for checking this kind of system. And the Dekker just is one typical way of making sure that hazards are checked. We have a range of mechanisms for addressing, for performing memory allocation and setting up address environments. And that makes, that allows us to do all these tests with all kinds of different allocated schemes, and again, can throw up a lot of bugs and problems. And we can get into false sharing, where we can pick contiguous bytes of memory and then try and test to see if two processes or masters are writing to different parts of the shared memory, the shared cache, and if they trip over each other or if that's detected by the system. And again, we can get into a whole range of false shared memory stress tests where we're setting up a broad range of scenarios to happen at the same time and create these false memory sort of scenarios that can trip over each other. Now, so that's just a really, really touching on the overall coherency mechanism. We can get more advanced. We can do virtual memory and start to get into paging and testing paging systems. Security is another area that often layers on top of coherency, especially if you're looking into different memory regions that can be, the access to which can be controlled. So this actually can be layered on top of coherency, and it shows how other system VIPs can be layered in and to create sort of more realistic scenarios where with coherency and security can be tested together. Okay, so I'm actually going to skip some of these slides because I know I'm going to run out of time. Basic, regular RISC-V testing can be layered on top of coherency testing, so load store tests, MMU, memory management unit tests, can also be built for RISC-V, for example, on top of some of these other coherency testing. Usually this is done, if it's ARM or x86, of course, the companies building those processors do this, but sometimes in RISC-V, it's worth doing this yourself if you're even building a core. And we can get into things like atomics, memory operations, directly run on memory, of course. Another aspect, when you layer this on top of coherency, it can create a lot of different issues. I'm just going to skip this. And finally, this just gives you a sense of the kind of coverage we can get. So this is actually an ARM window. It's actually the old Cadence Design Systems company building psychosimulators that was acquired by ARM. And you can see the top left is a pretty typical and pretty aggressive directed test structure where you see the addresses, data, and responses to memory all being layered together. On the right-hand side, the kind of automated testing that we're talking about here, where you're layering on top of each other all these different scenarios, can generate this kind of traffic. And this is what you need to kind of test one of these more modern SoCs, where you see the coherency dress in dark blue there, and the reads and writes coming out based on that. The kind of density of that is what you would expect to really torture one of these kinds of systems. So this is just to give you a sense of the kind of coverage that can be achieved. And I think, just a general sense where Breker is at is what we do is we take all these system VIPs, we synthesize them and go apply them across, virtual platforms, individual blocks, subsystems and systems, and even on final silicon. This is the nature of this portable stimulus. And that is the end of my presentation, Mike. I'm sorry, it's very rushed. I know this, it's a very complex subject. I just wanted to provide a taste of what's possible. But as I say, if anyone wants the full seminar on this, which is something we're even thinking of putting on YouTube, please feel free to contact us. Thanks, Mike.
Yeah, thank you. Thanks, Dave. Yeah, I know it's a huge topic that yeah, we wanted to get it into an hour and get 3 different points of view. So we'll put your slides and your recording onto the website, Dave, and then, but obviously there'll be contact details there for people who want the full hour if they want to hear some more. But thank you very much for fitting into that 20 minutes. Very useful. Thank you.